When talking about atmospheric conditions, weather patterns, how storms move, inherently we're going to have a discussion about climate and, by the end of this video, climate change. So I think it's best to start off with just a definition, what we talk about. When we say climate, this is a statement about the average state of the atmosphere. You're trying to say what's happening to the atmosphere across centuries or millennia. One quote that does a great job describing this is say that climate is what you expect and weather's what you get from the day to day. What's the average effect of the climate? What are these storms going to look like years from now? And there are a large range of factors that can affect the climate on these timescales. Even astronomical, geological, and biological mechanisms can change what's going to happen to the climate on these timescales of centuries. A perfect example of astronomical effects that can impact the climate on the planet is what's called the Milankovitch cycle. So there are two types of rotations happening here. You have the Earth's precession. Remember that Earth, between the axis between the Sun and the Earth is somewhere around 23 degrees. But on the time scale of about 23,000 years, the Earth will precess. Think back to the gyroscope that we did many videos ago. All right, so the Earth is precessing, going between 22 to 24 degree tilts back and forth. And so that tilt, remember, that has an effect on the seasons of the planet. On top of that, you have just the natural elliptical rotation. Now, this animation that's been playing is not to scale. It's exaggerated to highlight what's happening, but it does capture what's going on. We're talking about these elliptical rotations that are taking this time scale of hundreds of thousands of years. So the combination of these two create the Milankovitch cycle, which is about 40,000 years is the nominal values that are associated with it. And it's the change in the orbital position of the Sun and Earth and the angle the Earth's at that can impact the climate on these long timescales. Here is some data showing the amounts of methane and CO2 in the atmosphere. Now read these scales. The CO2, this is parts per million, and the methane, CH4, is parts per billion. And we're looking at age of the Earth in terms of thousands of years before the present. So 0 would be present day. This would be 100,000 years to 800,000 years. Right? So this long time scale. And we do see these natural cycles. We see these repeating cyclical patterns. This middle graph here, and that's just the temperature. How much the temperature is changing in the Antarctic. And we'll explain why these temperatures are measurements in the Antarctic. But the emphasis here is that what kind of impacts create these kind of cyclical patterns? Part of it's geological, just the shifting of our volcanic and tectonic activities. And there are biological factors. Bacteria, photosynthesizing plants, methane byproducts, and a human activity. We fall under this biological category. So it's a combination of these wide range of things that can create these natural cycles changing the climate on these scales of thousands of years. And that's going to be a key emphasis here. Thousands of years, 1,000-year cycles. So we're looking at oscillations like this that take on a time scale of hundreds of thousands of years. Let's look at the very end when we get into the present modern day. Look at the amount of methane, that's the red. Its peak was probably around the 800 parts per billion. Now look to modern day where it spikes to almost 1,800 parts per billion methane in our atmosphere. Similar to the CO2, we see these ranges. 260, 180 min, 300 peak here. And then we get to the modern day when the scales go up to 400 parts per million. And this is indicators, one of the reasons why we are concerned about global climate change. Now, obviously, how do we know the amount of methane and CO2 in the atmosphere? We don't have technology, we don't have tools or time travel to take sensor measurements at those times. So the way we do that, how do we measure the climate of the planet? Well, you look at gases trapped at the poles. This picture here is a mapping of previous ice ages, how much of the planet was frozen in that last ice age. And the emphasis here is that when that material freezes, it traps any gas sediment in that area. And as layers build on top of the ice, it goes deeper and deeper in timescales here. So by going to, say, Antarctica, drilling a hole down into the ice and pulling a sample of ice out there, and seeing, well, what are the ratios? What percentages of different gases are we going to find there? By looking at those ice samples, we get a picture of what the atmosphere looked throughout the different ages of the planet. This follows under the subject of what we call paleoclimatology. It's just a study of the Earth's climate throughout its history. And what we have found is that through the thousands of years, yes, you do see these cyclical patterns people can reference. But our climate can be very sensitive to changes in temperature. And from the start of the 20th century, we see these trends and these different types of gases, CO2, methane, now even some nitrous oxide. We see these levels rising drastically within the last century. And the key emphasis is the time scale of these changes. Look at these variations over hundreds of years, and then come down here. We've got about 1,000 years of data here, and then the spikes happen within the last century or so. So based on the data that we've collected, we're building up this case for climate change. One more. This is from climatenasa.gov, a site dedicated to putting out what is the evidence and information about climate change. And here we see the data again. Yes, you can see cycles. You'll often hear references of, oh, the planet has these natural cycles. And it does. You very clearly can see cycles in the data going through hundreds of thousands of years. But if we look at the trend within the last century, the spiking. That's the plot of CO2 in parts per million in the atmosphere. The trend has gone up drastically within the last century. Yes, there are cycles in our climate. The climate of this planet does have these cyclical patterns over these long time scales, hundreds of thousands of years, not a century. So this is the case that we're building up towards that to be definitive. Yes, there is climate change happening on the planet. So as a statement, a matter of fact, yes, the scientific evidence for warming of the climate system is unequivocal. And this is from an intergovernmental panel on climate change. Multiple nations were working on this. And these bullet points list off some of the aspects of how we definitively know that there is climate change happening on a rapid timescale. Obvious examples are, say, the global temperature rising, the glacial retreats, sea level rising. But we also see things like ocean acidification, extreme events, the frequency, and the intensity of storms, the big hurricanes that we see. We're seeing bigger storms happen more frequently. So this is all the arguments for, yes, there is climate change happening on this planet, and it is human driven. I don't want to leave us on a sour note here. This isn't about what's this a good or bad thing. This is just a statement of facts. And with some insight here, I think we have some positive outcomes that we can talk about this. Related to these discussions about climate change, how the atmosphere changes, let me go tell you a story about the ozone hole. This was discovered in the 1970s, and it was a combination of two factors that led to this big hole in the ozone layer. So by ozone, we mean the amount of O3 found in our upper layers of our atmospheres. And we love ozone because when ozone's forming our atmosphere, UV rays are being blocked. It is reducing the amount of ultraviolet radiation that's hitting us, and we are very susceptible. We can suffer damage from UV rays. So the two factors that led to this ozone hole. There was a 4% reduction of ozone found in the atmosphere, and coming back to these cycles here, we were in a larger springtime decrease in the stratospheric ozone. Just one of those natural cycles. So the combination of these two was producing this big holes in the ozone layers, and studies found that it was directly linked to man-made chemicals. Human-made chemicals was a factor in this depletion. By 1989, the Montreal Protocol ban was put in effect, and this was agreement from multiple world governments saying that we are not going to produce any chemicals that fall in this category of ozone-depleting substances. These are things like hydrofluoric chlorides, CFCs, halons, a bunch of refrigerants, propellants, and a wide range of others. And anything that was identified as being these ODSs was banned. In 1989, it was an agreement by multiple governments of we are going to stop letting people produce these things. Here's the aftermath. By 2000, about 20 years later, 11 years later, about 11 years later, we are starting to see the ozone is being replenished. We actually see the trends, it's recovering. We expect by around 2080, it'll be at the pre-1970 levels of ozone layer. So, positive thing. We identified a problem. 1970, we discover there's a problem. We're starting to understand it. Within about 20 years of that, we've come up with protocols. We've identified the issues. We've taken action to try and fix it. And it's working. We are replenishing the ozone layer that our actions inadvertently harmed. And that's the positive outcome, that we can take action to correct, remedy, change the things that are causing these problems, these issues. So once again, just a statement of fact, humans have an impact of the climate of the planet. This is not a statement of it being good or bad. We can talk about things of how we depleted the ozone, but also we're working to replenish it. You can talk about the range of plants that have been decimated or placed or cropped otherwise, where we've devastated forests and the places where we've planted forests. Right? This is not a statement of politics. This is not a statement about ethics. This is just a recognition that humans are a major driver of the climate of the planet now. Some people have proposed calling this the Anthropocene epoch, putting this human aspect to the epochs of the ages of the planets. Looking at the average temperature of the planets throughout about 2,000 years. Once again, there's those cycles that you'll often hear cited, examples of the variations in the temperature. And the shaded regions, those correspond to errors in the estimates. You have to, when you take a data measurement, you don't know it perfectly, so you put estimating bars. You estimate how certain you are about the value. So that's what these shade regions are. And the emphasis is, yes, we do see these shaded patterns. We do see these changes and fluctuations. Specifically, this is a plot of temperature difference from year to year. So we do see these cycles, and there is some uncertainty in the measurements, but look at the trends. Even here, this flat line. If I take the most extreme temperatures every time, we'd see cycles trend a little bit, but then we get into the last century, and we are still spiking high above from the previous 2,000 years. If I break this red curve here, that's just blown up into the one on the right, and we see the trends going. We keep finding that the hottest years on account are happening in the 2000s. Now it's the 2010s, soon it'll be the 2020s that we keep finding the hottest years on record. So here's the emphasis. We are dealing with a complex issue. Climate change is not the result of one person. It's not the result of, or any failures of a specific government, of a specific nation, a specific group of people. This is a global issue. And we can't just pretend that it's not happening, try and argue about, well, these little variations in the data means that it's just a natural cycle of planets. No. Look at the century of data. We see these trends happening rapidly, and it is human driven. But think back to what I said about the ozone hole. We drove that hole in the ozone to create with the chemicals we were producing. But we as societies also took action to correct that. And we can do the exact same thing with climate change. We have the opportunities, the capabilities. We are an intelligent civilization, and we have the willpower to change our behavior, change what is producing these large spikes. A remedy will not come instantaneously. Go back to the ozone. It took almost 20 years before the damage done to the ozone recovered, but it can recover. And the same thing's true about climate change. We can take actions, start changing how we produce things, where things are being manufactured, how we get our energy, and we can correct for the human-driven climate change. And in the process, innovate, make new technologies, get new types of energy sources. This doesn't have to be a sour, doesn't have to be a dire end of the world consequences. This can be a positive thing. We can actually innovate, make new technology to approach these new problems. And that is a big motivator in science. We take a complex issue and we try and tackle it. And in that process, we make new discoveries, invent new technologies that betters humanity. So summarizing everything we've talked about in this section 9, the terrestrial planets all initially had a primary atmosphere, but they lost that. That primary atmosphere was hydrogen and helium. All of terrestrial atmospheres are composed of what we call secondary gases that were trapped underneath the surface of the planet and liberated from, say, tectonic activity, or planted there by comets and meteorites crashing in. Greenhouse effects is a warming of the planets. You have CO2, water. These are our primary examples. Methane's another one. But different types of molecules that are really good at absorbing infrared radiation and bouncing it back towards the surface of the planet, warming the surface. Earth would be a frozen tundra without any greenhouse effect. So we do need some amount of greenhouse gases to make the planet hospitable for us humans. On Earth, ocean, and so the water and biological life prevented greenhouse gases from having a runaway effect, like how Venus is superheated. We talked about how Hadley circulation describes the movement of the air across the planet, and how the rotation of the Earth, the Coriolis effect, complicates that simple Hadley cell into the westerlies, easterlies, all the trade winds that we see on the planet. And that, yes, there is human-made climate change. It is a complex issue, but it's one that we as societies are set up to tackle and solve. So that, we'll call it in section 9, and I'll see you all next time.